Okay, so thank you very much for the invitation and for the presentation. It's my first time in the Czech Republic and also first time in Brno. I had some time to walk yesterday. It's really beautiful here. And I actually found out last week from my mother that my grandfather that I never met, he died before I was born, spent some time in Brno over 100 years ago. So she was excited that I was coming here. Anyway, what I want to talk about today is kind of recent advancements in our understanding of arithmetic functions, specifically multiplicative functions, which I'll explain in a minute. It's kind of a nice time to talk about it. The advancements are built on very major advancements in the last 20 years or so in ergodic theory, in number theory, and in additive combinatorics. So it's a nice time to tell the story, and it's not over yet. So as you'll see in the end. So who's the Mobius function? It's a very famous, well-known arithmetic function. It's defined on the natural numbers. It's given the values 0, 1, and -1, depending on the number, the parity of the number and parity of the prime divisor. So it takes the value -1 if n has an odd number of prime divisors, distinct prime divisors. It takes the value 1 if it has an even number of distinct prime divisors, and it's 0 on any number that has that is not square free. There is some square of a prime that divides it. And why is it a very important? I want to convince you that this is some function that's worth looking at. So here's like a basic fact you can notice about it. What it's called a multiplicative function. So multiplicative function in number theory means that the value at n times m is the value at n times the value at m, as long as n and m are coprime. Okay, so that's multiplicative. So that's a nice arithmetic property. And why is it very interesting? Well, it's very strongly related to the prime numbers. So there's probably the most well-known theorem in analytic number theory is the prime number theorem. And prime number theorem tells us that the number of primes up to n is roughly n over log n. This is about 100 years old, or maybe more than 100 years old. Apparently this is elementarily equivalent to a statement about the Mobius function. So a statement about the Mobius function having cancellation. So if you look at the sum of the Mobius function, sum of mu n up to n, then mu of n takes the value 0, 1, and -1. So ignore the zeros for a minute. So it flips between 1 and -1. And this prime number theorem is equivalent to the statement that it takes roughly the same number of values times the value 1 as the number as -1. So, and roughly half the numbers have an even number of prime factors, distinct prime factors, and the other half, an odd number. So that's one thing that might tell you that this is an interesting function to understand. Here is another. There is a very, very famous conjecture in number theory. This is hypothesis. The Riemann hypothesis is a statement about. It's elementarily. I can't say this word. Elementarily equivalent to a statement about a stronger statement about this cancellation in the sum of the Mobius function. So what does the statement say? It tells you a little bit, some kind of nice randomness property about the Mobius function. If the Mobius function was a random drunk, like walking on the real line, and it would, flip a coin, walk left or right, plus or -1, then we expect to see square root cancellation. So Riemann hypothesis is like saying Mobius is like a drunkard, something, walking on a line. So the title of the talk is about the Mobius function, but really it has a friend, which is called the Liouville function. Liouville function is almost the same as the Mobius function, but it's what is called a completely multiplicative function. So what does completely multiplicative say? Well, rather than just satisfying the condition that mu of n times u of n is equal to mu of the product on numbers that are co-prime, we now know that this is a completely multiplicative function would satisfy this for any integer. So really what you need, if you want to understand a multiplicative function, all you need to do is define its values on the primes and then extend it multiplicatively. So here's the easiest thing you can do. You define it for each prime to take the value -1 and extend it multiplicatively. Then if you have if you're square free, then you get the same value as the Mobius function would give you. And if you're not square free, then here you get some value and Mobius will give you 0. Okay, so the Liouville function differs from the Mobius function on the square free numbers. On the it's the same on the square free numbers, and it differs on the complement. So and the square free numbers are kind of easier, so they're not so difficult to understand. So instead of studying the Mobius function, sometimes it's easier to study the Liouville function. It takes only 2 values. It's completely multiplicative, but all the statements that I say about the Liouville function, similar statements can be extracted for the Mobius function. So although I said signs of Mobius, I'm really going to talk about signs of Liouville, but you should know that they're very, very closely related and one can pass information from one to the other. So for example, prime number theorem, the same as before. Prime number is equivalent to, I'm not going to try the word again. It's equivalent to cancellation of the sum. And Riemann hypothesis is the square root cancellation. Okay, it's like that. It's Liouville walks like a drunk on the line. Okay, so I hope at least maybe I convinced you that this is a function that's worth looking at and trying to understand. There's this vague principle which is called the Mobius randomness principle, or we should call it maybe the Liouville randomness principle. It appears in an analytic number theory book by Iwaniec and Kowalski, and it's called. It says something of the following. It says that this function, this Liouville function, should not correlate with any structured sequence. Now, it's very vague because. So what was this principle? What did this principle look like? Well, it's something like, show me the sequence, I'll tell you if it's structured, and then if Liouville should be orthogonal to it or not. Okay, so this is basically trying to say that Liouville should be orthogonal to something that has some structure or some low complexity, and about already 15 years ago or so, Sarnak tried to formalize this randomness principle in a really beautiful conjecture, which states the following. So he suggested that maybe we can associate to this structured sequences. So structured sequences should correspond to sequences arising from low complexity dynamical systems. These are systems of entropy 0. So let me say it and then explain everything. Well, I at least want you to come out of here understanding what the conjecture is, and then also what we know about it. So the conjecture is that lambda n should be orthogonal to any sequence arising from a dynamical system with a 0 topological entropy. So let me decipher what this conjecture means. So first of all, what is a topological dynamical system? Well, you start with a set X, a topological space. So you have X, a compact metric space, and you have a continuous map T from X to X. So this is what you need for a topological dynamical system. People are usually interested in what happens when you apply T. If T is from X to X, you can apply it over and over and over again and try to understand its orbits. So sequence, what does it mean for a sequence to arise from a system? Well, you can fix a point, x, inside your system and choose some continuous function, f, and then follow f along the orbit of the point x. So you look at an, the sequence that I get, is the value of f along the orbit of the point x. You fix a point x. Okay? Cool. So that's the sequence arising from a dynamical system. And finally, what does orthogonal mean? That's just saying that asymptotically, if I correlate lambda with this sequence coming from this dynamical system, so lambda n f of t to the nx, then I should exhibit some cancellation. So this is, if I look up to n, this is little o of n. Okay? Almost done. There's only one important thing missing, and that's a zero entropy. And rather than giving you an exact, so zero entropy is something about the complexity of the system. So it tells you that something about the rate of growth in the number of distinct orbits. But rather than giving you a precise definition, let me try to explain it for the systems that will interest us, or for okay. So here is a topological entropy described in the context when, suppose I look at the sequence space 0, 1 to the n. Okay, so look at all possible sequences of 0 and 1. That's a compact metric space. Okay? So within it, I can take x to be some closed subset. Okay, so suppose x is now a closed subset of 0, 1 to the n. No dynamics at the moment. Okay? What is a point inside this set? It's really a sequence, right? A point inside this 0, 1 set is a 0, 1 sequence. At each point n, I either put 0 or 1. I can think of this is the space of all 0, 1 sequences. Okay? Good. On this space, on X, there's a very natural map, and that is the shift map. You take a sequence and you shift it to the left. So here's an example. Suppose you take the sequence 0, 1, 0, 0, whatever is written there, and your sequence starts at 0 and goes on through the natural numbers, and the operation you can do is shift it to the left, so you lose the first digit. Okay? This is a continuous map for this sequence space on 0, 1 to the n, and if you take some subset x, like I described before, the closed subset that is invariant under this shift operation, then together you get a topological dynamical system. Okay? So here is what I have. I have some subset of the sequence 0, 1 sequence space, and I'm assuming that this subset is invariant under shift. Okay? And this subset, if it's invariant under shift, it gives me a topological dynamical system. So far, okay? Cool. And now what is the entropy? How can I calculate the entropy of this system? Well, I can ask myself, I can fix a k, so fix a window of size k, okay? A window of size, I look only at k coordinates, and look at all the points you have inside X, inside the system you have, and take a point and look at this window of size k and move it along the sequence and try to see what patterns of zeros and ones you see. Okay? Do that for all the points in the system. Okay? All the points in your system, you take for each k, you take a window of size k, and you measure how many different patterns you see. Okay? So here is an example. Suppose you, and you measure the growth of this in k. You measure the logarithmic growth of this in k. Okay, so here are two extreme examples. So suppose x was the full sequence space, 0, 1 to the n. Okay, then if I fix a block of size k, I see all possible sequences. Then sk of x is 2 to the k, and my entropy is log of that. Okay? But if, for example, if I take here's the kind of most extreme example to the other direction. I could, the most extreme example is maybe to take a trivial system, just a point. But, okay, let's do one further than that. I can take, say, the 2 points, the 0, 1, 0, 1, 0, 1, 1, 0, 1, 0, 1, 0. That corresponds to the even and odd numbers, even and odd sequences. Then this is a shift invariant system, but then how many blocks do I see? Well, 2. No matter what, except for any k greater than 2, I see at most 2 blocks. So the entropy, there is no exponential growth. The entropy is going to be 0. Okay? So basically, this is the way we should try to think of it. We're trying to count the number of different patterns we see inside the sequences in our system. Okay? So back to this conjecture of Sarnak. So Sarnak says lambda n, this Liouville function, this multiplicative function, should be orthogonal to any sequence arising from a system like the system I described. That's enough to think about these systems. Okay? And I remember seeing this. So I heard this conjecture when he came up with this, like, I don't know, 15 years ago or something. So I was already a mathematician then. And I remember thinking, why should this be true? This seems like it's a wonderful conjecture, but at a first glance you can't really understand why something like this should be true. And the thing is that apparently it follows from a very other well-known conjecture. So there's a well-known conjecture in number theory, which is called Chowla's conjectures from 1965, and Chowla's conjecture is about the self-correlation of lambda with itself. Okay, so I fix integers a1 through ak, different integers, and I look at the lambda n plus a1 times lambda n plus a2, and I look at the multi-self correlation of lambda with itself, and the conjecture is that this should exhibit cancellation. So if you think it's this Chowla conjecture, the reason many people believe it's true is that it's kind of a lambda version of the prime tuple conjecture. There's a very well-known conjecture, which is like the one most people know is the twin prime conjecture. People conjecture that that if there's no reason to not see some pattern in the primes, you should see it. There's no reason not to see infinitely many pairs of difference too. So twin prime conjecture says that, and says that for any tuple. Fix any k tuple. If there's no silly reason why you can't see it in the primes, for some divisibility reason, or like you can't see n plus 2, n plus 4, because one of them is divisible by 3. But if there's no silly reason, then you expect to see any pattern infinitely often in the primes, and there's also a conjecture to how often you should see that. And this is kind of the lambda version of this conjecture. Okay, so many people believe that this conjecture is true, and what Sarnak showed at the time is that Chowla's conjecture, this well-known conjecture that people believe, actually implies his conjecture, this conjecture about the zero entropy, the lambda being orthogonal to zero entropy. So now that makes it more believable. And from people coming from dynamics like me, maybe the first conjecture is more attractive, or at least one can try to think how one might try to attack it. So let me tell you about the first instances of what people first try to do. So we have this conjecture. So on Chowla's conjecture, okay, still wide open. But here's Sarnak's conjecture again. Let's try to test it on very simple dynamical systems. So the simplest example, and this is the Liouville system. So what is the Liouville system? So remember the sequence lambda, it takes plus minus 1 value. So instead of looking at the sequence space 0, 1 to the n, I can look at the sequence space plus minus 1 to the n. Okay, that's all sequences of plus minus and 1. Plus minus 1. Okay, so lambda is just a point in this space. Now, if you give me a point in a sequence space, I can develop from it very easily a dynamical system. How can I do this? I can look at this point, look at all its shifts, translate it, all its shifts to the left. I get lots of points. Look at the closure of this. This is a closed invariant set. Okay, so if you give me a point, I can extrapolate from it a dynamical system. like kind of the minimal system it belongs to. If it belongs to this system, then all its shifts have to belong to the system, and it's closed, so the closure has to be in this system. So this is like the minimal thing you should be looking at if you're interested in this lambda dynamically. So this is x lambda. So I look at lambda, I look at the shift t, the shifts to the left, I look at the closure. So I get a topological dynamical system. And on this system, I have a very interesting continuous function, which is the window at 0 function. So think of the function that takes a sequence. My sequences start at 0. That's for convenience of indices. So think of the function that looks at a sequence and tells you what stands in the first coordinate, which is the 0 coordinate. Okay, so this is this function f0. F0 of some point xi tells you the first digit of this sequence. So it's a continuous function in topology, in the product topology on the system. And it's very nice because if I apply it, if I take a point xi and I apply this f0 to t to the n xi, that's just shifting to the nth point. This is exactly giving me the sequence at the point n. Okay, so f0 of t to the n of a point xi is just xi of n, the sequence at the point n. Why did I want to bring this? So for example, if I do this to the point lambda, f0 of t to the n lambda, that's just reproducing, I can reproduce the sequence, it's the sequence lambda as the function f, as a sequence arising from the system x lambda. Does that make sense? Remember, this was the conjecture, is for any, I can reproduce lambda n, the sequence lambda n, as a sequence arising from its system. Okay, in the way that I described how a sequence arises from. And I claim that if you do that, then Sarnak's conjecture would imply that the entropy of, if we believe Sarnak's conjecture, then that would imply that something about the number of sequences I see. It would imply that the entropy of this system has to be positive. Let's see why this is true. Well, if suppose it had 0 entropy, okay? If this system x lambda had 0 entropy, then it would fall into the category of, into Sarnak's conjecture. So lambda has to be orthogonal to it. So I should have that lambda n, f0 of t to any function, not only f0, but for any continuous function, but in particular for the function f0, this thing should be little o of 1. But this is just lambda n squared, okay? So definitely not little o of 1, okay? So if Sarnak's conjecture is true, that means that the number of patterns of plus minus 1 patterns I should see in Liouville, that should grow exponentially, okay? Chowla's conjecture actually tells us that it should grow, I should see all patterns and grow in the correct rate. Entropy doesn't tell you, if you see it once, it's sufficient for the entropy. It doesn't care about how many times you see it. But Chowla's conjecture is much stronger than that, okay? It demands that you see each pattern in the right frequency. Okay, so Sarnak's conjecture, again, I keep it in the background, so remember it. At least, this is something you can take home with you. And I said, this is what I started talking about before. I want to give you some instances of when this conjecture is true. Let's start from the easiest dynamical system we can think of. That was my pre-example. Okay, I can take the trivial system. If I take the trivial system, it has just a point, trivial action, nothing in it, then what is any continuous function? And this is just a constant. It's just saying that lambda should be orthogonal to constant functions, and which is just saying that it should exhibit some cancellation. So the trivial example is the prime number theorem. Okay, that's the main theorem in analytic number theory, is the base case for this conjecture. Okay. So if we understand like the trivial, okay, what do we do? We start with the trivial example, that's okay. Then we go to the next example, which is maybe a periodic system. So like the even odds we had before, or in general, Z mod MZ with +1. So I have a periodic system. And to claim that lambda is orthogonal, so what are continuous functions coming from periodic systems? These are just periodic sequences. So this is really just saying something about the cancellation lambda exhibits along arithmetic progressions of some fixed gap. And the fact that one understands that, that's also a well-known theorem. That's the prime number theorem in arithmetic progressions. So there's a well-known theorem that tells you that every legal arithmetic, for primes, it tells you that every legal arithmetic progression has its fair share of primes, and this is the lambda version of this theorem. Okay, so we go up a little bit in complexity. So we go to the next stage, is the next simplest theorem system we can think of. That's it's a circle rotation. It's I can write it as R mod Z or S1 or the circle. So I look at R mod Z and I look at the shift by alpha, which is, if alpha is rational, then I'm back to the previous case. But if alpha is irrational, then this shift, all these orbits are equidistributed inside in the interval, and I can try to understand what the conjecture means for this system. And really, this system, if you want to understand continuous functions coming from it, really you just need to understand linear exponentials. And for linear exponentials, this is also an old theorem of Davenport from the 30s, I think, of the previous century. Yeah, we are not in the 30s yet here, so I can still say 30s, and that's well defined. Okay, so this is also was well known. So and here is maybe the next level of complexity that I'm almost stopping at. Okay, I have two more systems to describe to you. One is this system, which is called a nil system. A nil system is a dynamical system. It's one level complexity above this circle rotation that I had before. So before I had an abelian system, now I have instead of looking at the definition, think of this system that I wrote over there. So think of X to be the Heisenberg group over R. So these are matrices that have 1 on the 3 by 3 matrices, like in the picture. They have 1 on the diagonal and elements from R on top the diagonal. And inside this, I have a lattice, which are the Z points. I look at all kinds of matrices of the same form, but I have only integers there. And if I look at the quotient space, that looks like the quotient space looks like a torus, a two-dimensional torus, and there's like a circle above each point. But but it's not the addition there is not like a three-dimensional torus. So this is called a nil system. So this is X. X is this homogeneous space, and you fix some matrix, and you act by this matrix. Okay, you look at A to the n. If you have some homogeneous space, some quotient space, of a group, you can just act by the element of the group. If you were just ignoring the top coordinate and just looking at the off diagonal coordinates, that's a two-dimensional torus, and the same case as before. Okay, not a instead of one-dimensional torus, two-dimensional torus, but the same case as before. But now we have this extra twist in the third coordinate, and the reason these and the fact these are really important systems. And first of all, the fact that lambda is orthogonal to them, to sequences coming from these systems, was proven by Green and Chow in 2010. I think that was prior to Sarnak's conjecture. It was one of the motivations that he had for this conjecture. And these systems are extremely important. They played a very important role in solutions to linear equations and primes. They play an important role in understanding how to solve linear equations in subsets of integers. So they're an important test case, but still the dynamics of this test case are relatively easy. So the last example I want to give is that of the horocycle flow. So horocycle flow is another important dynamical system. You take SL2R, so this is 2 by 2 matrices, determinant 1, and you take some lattice, say SL2Z, then it's not compact, but say take some lattice, and you act by by the matrix 1, 1, 1. Okay, so you shift by this matrix 1, 1, 1, and you look at the orbit of a point in this system. This is called the horocycle flow, and back 12 years ago, Bourgain, Sarnak, and I showed that the horocycle flow, this system is known to have zero topological entropy, but the dynamics is rather complicated. Understanding what the orbits look like involves huge theory that was developed by Marina Ratner. And so this was like an important test case for a non-trivial, for a system where the dynamics is complicated. But really what it hid inside it is a technique. This is what I want to try to explain, is how to turn this question from an arithmetic question to a completely dynamical question. So this is the observation we made there's an observation we made in that paper that apparently we discovered was already made before us by Katai and Debussy-Delange. And in a different language, they weren't thinking about this problem, so it was stated in a different way. But the observation is that if you have some sequence and you want to show that lambda is orthogonal to it, then what you really need to do is take any different pair of primes P and Q and check the autocorrelation of the sequence with itself. So I look along the P orbit, the multiples of P orbit, and the multiples of Q orbit. So I need to understand the sum of F of the system T to the P and the system T to the Q, and I look at them together. Okay, and this translates this question about this arithmetic question to a completely dynamical question. It's just a question in dynamics to try to understand. Let me formulate you a completely dynamical statement that this tells you. Right? It says that we want to understand when a sequence has this cancellation, when lambda n is orthogonal to f of t to the nx. And this criterion says that it's enough to show that for any pq, I have this autocorrelate. I have no correlation between the p orbit and the q orbit. Now, let me just rewrite the sum expression in a different way. So to look at I averaged instead. I looked at 1 over n. I averaged instead of just summing. So I want to look at f of t to the pn and x times f to the t to the qn. That's the same as taking the delta measure at the point t to the pnx times t to the qnx and evaluating it at the function f tensor f bar. Okay, this is tautology. There's just a different way of writing a mathematical state, this equation, this formula. And the nice thing is that once you think about it this way, then you can ignore the function and just look at the measures. You have a sequence of measures. These measures are the delta measures that are supported on the points t to the pn, t to the qn, and this kind of averaged measure. And the space of, this is a probability measure, and the space of probability measures is compact. So sequentially compact. So if I have a sequence of measure, there is a subsequence that converges to some measure. This measure nu that I get is some measure on the product, on x times x. So I started with an arithmetic question, and I'm now in the situation where I have a product system, x times x, and a product map, t to the p times t to the q, and some measure, a coupling of these two systems in the way that if I project on the left on one system, I get the system of t to the p, and if I project on the other coordinate, I get the system of t to the q. And I'm trying to understand what are all the possible couplings of these two systems. Okay, and sometimes it could happen that the only coupling is the trivial one, is the product coupling. Or I could try to just classify all the possible couplings of the systems and try to show that if I understand them, then I have an attack on the problem. And so this type of coupling, this is the terminology in dynamics. It's called joining. And this is how, for a long time, this is how I don't know, a long time. It's like 12 years since the, I don't know, 14 years since the conjecture. So I don't know, long is how long it's long. But for some time, the attack on this conjecture was via this method, okay? I can pick a system with zero entropy, could be very complicated, try to understand all the possible joinings it would have, all the possible couplings it could have for different P's and Q's, and show this, and then show that it satisfies this conjecture of Sarnak, okay? And we were there for a long time. Again, long. I don't know what long is, but then in 2016 came a new advancement in number theory, and this new advancement was done by Matomaki and Radziwill. I don't know if I'm pronouncing his name correctly. And what they did is they were studying self-correlation of the lambda function, but okay. Ignore the averaging for a minute. Look at fix h. If you fix little h, you look at lambda n plus h, say h was 1. This was just like a twin Chowla case, right? It's like the Chowla case when I had lambda n plus 1. So this we don't know. But suppose we give a little leverage, like we give us a little, how do you say, like a little rope. We give us a little bit of freedom in the way that we don't fix h to be 1, but we allow h to vary a little bit in some range, big H, and allow big H, we don't fix H. If we could fix H, that would be amazing, but we allow H to grow to infinity as slow as we want. This is what they showed. So think I'm looking at the correlation of lambda with itself in intervals of size, of a fixed size h. H could be very small. It could be log n, okay, as many times as you want, essentially constant in our finite life terms. But they showed that you still get cancellation in this form, and very quickly after that, Tao observed that actually. If you tweak your averaging form instead of normally in undergrad we always use Chizauer averaging. That's 1 over n, the sum of an. That's standard averaging. But there is a tweak of this kind of averaging. It's called logarithmic averaging, which says that instead of summing up to n and dividing by n, I look at the sum of an over n. And divide that by the sum of 1 over n, which is log n. Okay, so this thing is called logarithmic averaging, and if we and it's easy exercise, first year exercise, to show that if you understand the convergence in the Chizauer averaging, then that implies convergence in the logarithmic averaging. But the other way around is not true. Okay, so he showed that. You can take their result, and if you allow this easier averaging, this logarithmic averaging, then you can actually get something like the log Chowla, the twin Chowla conjecture. So I fix h now, okay? It's like h equals 1. I fix h, and I look at the logarithmic average of this thing. I look at 1 over log n, and I sum whatever I need to do over n. Okay, so if I do that, then I can get I can get a log Chowla conjecture. So a log two-point log Chowla conjecture. So it's only for pairs. I wanted to get it for any length, but let me tell you. Okay, so here's the caution. So logarithmic averaging is a serious relaxation. So if you try to prove the logarithmic version of the prime number theorem for Liouville, instead of summing lambda n, summing lambda n over n, that's an exercise. That's not a difficult exercise, okay? But so logarithmic averaging is a serious relaxation. It's really it's not something trivial, but the good news is that for the entropy, if you're just interested, for example, in the question of positive entropy or the number of sign patterns, then that's okay. Doesn't bother you. You don't care. Excellent. So this is the logarithmic two-point Chowla theorem of tau. And motivated by this, you can weaken all the conjectures. Instead of looking at Chowla conjecture and Sarnak conjecture, you can look at the log Chowla conjecture and the log Sarnak conjecture, which is just replacing the regular averaging by the logarithmic, the easier logarithmic averaging. So this is the log Chowla conjecture and log Sarnak conjecture. And Tau, in the same spirit of, in the same way that he, same idea that he used in the theorem for his two-point Chowla, he showed that these two conjectures are actually equivalent. Okay, so without logarithmic averaging, they're not equivalent. Chowla's conjecture is stronger than Sarnak's conjecture. But if you allow the relaxation of logarithmic averaging, then these two conjectures are equivalent. So if you can solve the log Sarnak conjecture, then you, or the log Chowla conjecture, each of them would imply exponential growth in the number of patterns. Okay. Okay. So back to, so I said there was a breakthrough in analytic number theory. This is this theorem of Matomaki and Radziwill, and an extra idea is called an extra entropy idea that came from the theorem of tau. And but let me go back to dynamics. So the whole way this thing develops is jumping between dynamics, analytic number theory, and you'll see soon also additive combinatorics. So we jump between these three, we juggle the three of them, and each time make progress from a different direction. So let me show you. So I claim that you can take this Matomaki, Radziwill, and tau theorems and actually prove that they have a dynamical content. They really say something about this Liouville system that I told you about before. So this was the theorem of tau. This is the two-point Chowla theorem of tau. And recall this Liouville system, the system x lambda. I took the point lambda, I looked at its orbit, I closed it. I want to study the entropy of this system or something about this system. And to this, so before I just had a topological dynamical system, right? I took lambda, I took its orbit, I closed it, I looked at all points, the system that I get. Now, I can take this system and add on top of it a measure. How can I add a measure? In the same way I showed you before, like in the same way that we did for this joining idea. You look at the delta measures at the points of the orbit. I look at the delta measures along the orbit, but instead of looking at regular Cesaro average, I logarithmically average. That's all. Like the standard way you would do it would be 1 over n without the little n over there. But instead I take logarithmic averaging of the same object. This is also a sequence of probability measures. If you have a sequence of probability measures, there's a subsequence that converges. Okay? Now I can look at all the systems. I get lots of systems. I can have lots of subsequences. They can give rise to many, many different systems, systems with a measure. But in each one of them, I can look at this special function f0 that I had before, this continuous function that looks at the 0 coordinate. And the dynamical content of this theorem of tau together with Matomaki and Radziwill is some statement about the fact that this specific function is orthogonal to the eigenfunctions of this. No matter what system you get at the end, no matter what measure, whatever system you get would produce to you some eigenfunctions of the system, and f0 must be orthogonal to these eigenfunctions. Okay, so it's some dynamic. Conjecturally, all the systems you get are Bernoulli, like plus minus 1 to the n. They behave like this is the conjecture. Chowla's conjecture would tell you that no matter what, if you knew it for real, or the log Chowla conjecture in this case, would tell you that you always get that no matter what sequence measures, no matter what subsequence you take, you'd always get a Bernoulli system, a plus minus 1, like the free system, the coin toss system. But we don't know that. What we do know is this thing about the eigenfunctions. Actually, this idea was pushed very, very further, I don't know how to say, by Frantikinakis and Host in 2018, now building on things on major results in ergodic theory and in additive combinatorics. And what they showed is some really interesting fact about this Liouville system. No matter what system measure you get in the end, you get some system. And that system has ergodic components. Think of it as kind of the prime factors in some sense of this system. Like the building blocks of this system are made of two types of systems that we understand. Either they're nil systems, like I told you, this nilpotent, these Heisenberg systems are very important, which we already understand, or they're like Bernoulli systems. They're like Bernoulli. Bernoulli is like a coin toss. I always say coin toss, so like a coin toss system. Okay, so it gives they give a very strong structure theorem. And this builds on everything that was known until then, to some extent. So what does this build on? It builds on the fact that these nil systems play a role in trying to understand ergodic averages. So those are results from 2005 and 2007 by Host and Cry and myself. And then this inverse theorem for the Gowers norm, which is kind of a parallel theorem to the theorem that I described to the nilpotent structures in ergodic theory that appears in combinatorics. So nilpotent structures appear as in combinatorics as well. It builds on this new result of Matomaki and Radziwill about short averages of multiplicative functions, and this entropy, this new entropy argument of tau entropy decrement argument. So it takes everything that we've discovered, that we have like in the last 20 years, and puts it all into one nice big theorem. And as a corollary, they're able to show that the log Sarnak's conjecture holds for any system that is uniquely ergodic. So uniquely ergodic means that there is only one limiting measure. Okay, and that doesn't, whatever subsequence you took before, you always get, if you take whatever subsequence of measures you take, you always get the same system. So let me tell you what this means. This last theorem that they say has something, I want to wrap up. I come back to the original question I started with. I called the lectures sign patterns of Liouville. So we're back to the question of, I'm trying to understand what sign patterns I can see inside this Liouville, what kind of patterns of plus minus ones I can see. So S lambda k, this will be the number of blocks of size k that I see, okay? And a corollary of this Frantikinakis-Host theorem is that these sign patterns grow at least linearly. So think about what we didn't know. We knew almost nothing. We didn't even know that they grow. We want to show that they have exponential growth. But until this theorem, we didn't know that they had better than linear growth. Okay, so their theorem, so how does it imply? In a kind of a similar to the argument that I described before. If you have too few blocks, if sublinear growth, then that means you're not exactly uniquely ergodic, but you have at most finitely many ergodic components, and then by the same argument that I described before, you get a contradiction. You get that lambda has to be orthogonal to itself. So this is a corollary of their theorem, and it was pushed further by McNamara to show that actually you grow better than quadratic, and very recently, in joint work with Matomaki, Radziwill, Teravine, and Tau, we showed that actually you grow super polynomially. So we want exponential, not there yet, but we grow better than any polynomial. But that doesn't use dynamics. That goes back to additive combinatorics. So this is like the best thing we know to date. Okay, best thing we know to date is that we grow super polynomially. We believe that we grow exponentially. In order to try to attack this conjecture, we need to really understand self-correlations if we wanted to prove the full Chowla conjecture, then we would need to fix some h, look at an arithmetic progression with gap h, think of h as 1. This is what we would want. If we could, h were equal to 1 or any, and we would be able to understand what lambda n plus 1, lambda n plus 2, at lambda n plus m. If we could understand this averaging, then life would be awesome. Okay, then we could prove Chowla's conjecture. So we can't do that. But in order to prove this result that I told you, this super polynomial growth, we can relax this. And instead of proving that thing on top that I have no idea how to prove, we can actually, instead of fixing h to be 1 or some specific number, we can, like Matomaki and Radziwill did, we can allow a range for the h parameter as well. We would want it to be as small as possible, but for what we can do and for the result that I said about, we can take it to be n to the epsilon for any small epsilon that we want. Okay, so n goes along, so we fix a window of size n to the epsilon, and we study this question, we move this window and study this question along this n to the epsilon window. And in order to understand these kinds of averages, there is a machinery that was developed which is like local Gowers norms. It's like, I don't want to explain what Gowers norms are, but really they're kind of higher order extension of Fourier analysis for problems. If I were just interested in this problem for m equals 2, then this would be a question about local Fourier coefficients at scale n to the epsilon. But in order to understand it in full generality, these nil systems come in the picture. They're the higher order versions of Fourier analysis. And so we need to understand this kind of local UM norms of the Liouville function. And this is really, remember the result I told you of Green and Tau about lambda being orthogonal to nil sequences? We need the same type of results, but for short intervals. Okay, so we need to know the same type of results, but for intervals of size n to the epsilon. This is the theorem that we need to prove. I just show you that what it means for k equals 1. What is k? That's a good question. It's probably the m from before and 2, but for this is the easiest case is the easiest case is when there's no exponential. It's just 1. That's the Matomaki-Radziwill theorem, okay? In the interval of size n to the epsilon. It's like the system. We started from moving from constant system, then to periodic system. That's also understood. Then there is the circle rotation system. That's this one over here. So it's like local Fourier coefficients at scale n to the epsilon. So we need to show that we have cancellation for that. This is, I'm just writing to tell you that for this specific case, there have been advancements, very, 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 very recent advancements. So for this Fourier case, we need, not the Fourier case, we need the nil sequence case. But for the Fourier case, we were able to actually do better than n to the epsilon. We could do h to the e to the log n to the 2/3. And shortly after that, Miguel Walsh was able to push this to e to the log n, square root log n. But actually, very, very recently, Walsh was able to show that you can take h to grow like log n to the psi n, where psi n grows as slow as you want to infinity. So almost, almost power log, but not still power log. But that's conditioned on GRH. So you can decide, which conjecture you prefer, Chowla or GRH. If we could bring it down to log n to the epsilon, that would imply log Chowla conjecture, which would imply log Sarnak conjecture, which would imply positive entropy. So if there's still a gap between log n to the psi n to log n to the epsilon, and there's GRH hanging around. But other than that, we're getting, it's much closer than I think anybody thought we could get to. If you asked me, I don't know, like 2010, when I first heard about this conjecture, I would be completely, I have no clue that I would be really surprised to know that we've made it this far. I'm just saying that this is for the Fourier. You still need to push this entire machinery for nil sequences for this higher order Fourier analysis, but there's a lot of technology that was already developed for that. So I expect that maybe not to be the obstacle, but just first to figure out the Fourier case all the way to the end, and that's what we know. Thanks.
Thank you.